Okay, so Alright, so let's talk about tables. Tables, arrays, or objects, or matrices, or matrix in singular form. These are all names that I will interchangeably use to refer to tables. Tables are the variable type that we haven't talked about yet. They are like a way to encapsulate a bunch of different variables under one name. So if you have a variable named egg, a table is kind of like an egg carton where you can hold a bunch of eggs, and it's a lot easier to carry them around without making a mess. So it's one way to think about tables. A bunch of parentheses or brackets are going to show up soon. Just heads up that like in Lua, which is the programming language behind Pico-8, the curly brackets are the way to tell that you're kind of like setting up a table. So this line of code creates a table called egg carton, and it fills it automatically with 1, 2, 3, 4 numbers in the 1, 2, 3, 4 addresses of the table. You can put other kinds of variables in there. So just put a little bit of egg text in there. You can even put tables inside of tables. So here I have in the location 6 of, the key 6 of this table, thing that you put in to get the value out. So this is 1, 2, 3, 4, 5 is egg, and then 6 is a whole other table with a single item inside of it, and that's a bit of text called whoa. So how do we interact with this table? We can say, what will happen if we print the whole table? Table. So it just like over here, it printed it as square brackets table. It's not going to go into the table and tell us what's inside of it, because the print function doesn't really do that. But here we can use the square brackets. Notice that I'm using different kinds of brackets here to dial in an address of this table up above. So I can say, give me the value from the location number 1. And so here it's going to print it number 1. This is not very easy to see what's going on. So I'm just gonna clear the screen before I do my printing. And we'll make it a friendly 9. And I'm going to print this in 0. Okay, there we go. So 1 is the value of egg carton 1. So what would happen if we pass egg carton 5? Egg. All right, we knew that was going to happen because that's what egg is. And if we pass 6, table. But we have this, table, and we are selecting the 6th item from this table. So like this expression here is the same as like dialing into this particular table. So what if we doubled up on our addresses and we said 1? So notice now we have 2 sets of square brackets that we're putting on the end of this. We're getting the value number 6, and then out of that, which we know is a table, we know that this is going to return this table. We're going to say, now grab the first value from that table and print it out. And whoa, it worked. All right. What will happen if we ask for the second item in the table? Nil. It doesn't exist. So this is our basic table. We've been puttering in the sort of like training wheels land with our code up until now. These tables are a dawn of a sort of a big brain moment for us, because You've noticed that programming is all about keeping track of where things are and what they're doing so you can animate them. Tables in their many forms facilitate keeping a whole order of magnitude more things up in the air at any one time. You will hear me refer to tables interchangeably as tables, as arrays. This kind of a table is a very basic sort of like array, because its keys, its values that you plug in here are just numbers, and they're all in row, right? So there's like 1, 2, 3, 4, 5, 6. Those are the addresses of each of these values. It just so happens that 1, 2, 3, 4 are also the values of the first 4 addresses. Pure coinkydink. So over here on this next tab, I have created some sample tables for us, and these are actually frames of animation for a simple flipbook animation for these 3 folks here. This is Hrozgo, this is Amadeus, and this is Sned. So I have kind of like written in here 1, 2, 0, 3, 4, 0, which corresponds to 1, 2, 0, 3, 4, 0, 1, 2, 0, 3, 4, 0, and that is the flipbook animation I want this guy to have. So we're going to use our little table to figure out how to create a flipbook animation of these dudes doing their little like cycles. I would also like to use the SSPR function so I can stretch my sprites across the whole screen, so they're not like teeny tiny like this. So yeah, let's put some stuff on here. What is all this? Oh yeah, my egg cartons. Let's delete this. All right, function draw and function update int. So in here, we're going to put SSPR. Now, a first complication that we are stumbling upon here is that SSPR asks for the X and Y coordinates of the sprite sheet, and then the width and height of the section that we want to grab from the sprite sheet, right? But whereas like our sprite function just takes the index value of the sprite, and over here we have our like animation in just our index value of each sprite. So 0, 1, 2, 3, 4, right? So how do we convert this number 1 into 8, 0, right? Because that's what we need to be able to do, convert it into both an X and a Y value. And I'll use 2 fancy math tricks to do that. So okay, let's see. So we are going to be drawing like, let's see, my dude, and I'm gonna say face. My dude face is gonna be, for now, let's just make it 1. So it's gonna pull this Hrozgo here with its leg up in the air. So this is gonna be, we're gonna feed a value from this sprite sheet as we're animating at some point, but right now we're just gonna like draw a single sprite on the screen so that we know that one part of this thing works, and then we'll complicate it again. All right, so my dude face, and then I'm going to multiply it by 8. So that's going to give me, the first row's values, right? So this is 4, and this top left one is 32, which is 8 times 4. 32. So I know that will work for the first row. It will not work for the second row, because here I need that same 32, but I also need the Y to grow by 1, or rather by 8 pixels, to get it to that Y of 8. and we need to kind of like extract that 32 like as well from the same number 20 that we have there. So I'm going to use the modulus. I'm going to use the modulus. Modulus is this percent sign. It's like shift 5 on the keyboard. And modulo or modulus. Modulo is the name of the symbol, and modulus is what you're doing, or vice versa. Anyway, I'm an artist. I can be mushy with my terminology. Nobody's going to come after me. It's not like I'm putting these on the internet or anything. All right, so my dude face is going to be 20, right? And then modulo is going to give us not the value when we divide, but the remainder after we have divided by a number. So like if we divide my dude face by the number of sprites that we know happen in one row, which is 16, and then multiply that by 8, this is going to give us the x coordinate from this number. And then for the y coordinate, I'm going to use my dude face again, but instead of like dividing and taking the remainder, so what the dividing by the number of sprites of 16 here and taking the remainder means that like this is going to be the remainder of 0, this is going to be the remainder of 1, this is going to be the remainder of 2, because you're taking 2, you're dividing it by 16 and taking the remainder, which is 2, because there's a 0 times 16 in 2, and then the remainder is 2, and then you're multiplying that by 8, and so you're getting 16, right? And that is correct, right? That's our x. For the second row, we divide 18 by 16, or you know, that is 1. We subtract 1 times 16 from 18. That gives us 2. 2 times 8 is 16, and so we get the same value for the next row, and the row after that, and the row after that, giving it these values. So that is one, you know, the power of the modulus, right? And then for the y, we wanted to tell us how many rows we've had to skip, right? How many rows we have gone down, but we don't care about the remainder that we're going to get when we divide. So we could say divide by 16 and then floor this number like this. Floor this number and then multiply it by 8, and this will give us the height. But I'm going to give you another trick, like programming math character here. So this is the normal divide symbol right here. If we use the other slash, it will divide the number and then throw away the remainder. So it'll give us like a round integer how many times my dude face can be divisible by 16. And then we need the width and the height per here, right? Sprite width, sprite height, and that is in pixels, right? So I know that my dude height is going to be 1, and my dude width is going to be 1 to begin with. But notice that like this guy over here is actually too wide, so we're gonna make a little function that will accommodate him and his sprite situation. So my dude height, my dude width, my dude face. We're giving like we're collecting a bunch of variables, free floating variables here that are kind of related to my dude as we are drawing him on the screen. So all right, so now we have width and height. So here I'm going to say my dude width times 8, and then my dude height times 8. Again, because over here we have decided to use sort of tiles to describe how big our dude is, and over here we want that to be converted into pixel values. So instead of like, you know, doing this stuff ourselves, we're going to let the computer do it for us. And here, to help myself kind of see what's going on, I'm going to divide this into rows. So I'm just going to put the x and y in the first row, and comma, and then I'm going to put the rest of the stuff over here. So I'm still writing the SSPR function, but so that everything kind of fits a little bit better on the screen, I'm going to fold it a couple of rows. Okay, so then draw x, draw y, draw width, draw height. So this is where it gets really handy because we can stretch the sprite. So see, this one over here only allows you to draw it at one-to-one size, but this one you can draw it in any kind of scale here. All right, so let's draw it on the screen at a specific coordinate place. Let's give it my dude x, my dude y. And where do we want to put them? Let's put this guy at 20 or 95. All right, so let's draw my dude x, my dude y. And then for the width and height, let's use a scale. My dude scale, and let's draw 10 times. So here I'm going to say my dude scale times 8. So it's going to be 8 times as large as whatever. So this is the x coordinate as well. So I'm going to use the my dude width as well here. So in case we're using our double wide guy, our walking wolf, at that point it will also double it to match the width. So we're anticipating, we're thinking ahead. Okay, my dude scale times 8 times my dude width, and then I'm going to do the same thing for my dude scale times 8 times my dude height. So in case we had a double tall guy, we can draw him on the screen using this SSPR function. All right, my dude scale width, my dude scale height. And let's ignore the flip business for now. And this should draw a guy on the screen. It should draw Roscoe. Oh, let's clear the screen too. And let's, I don't know, clear it in 3. All right, hey, that's something. It's drawing. Oh yeah, I wanted to draw him at the 95 line, but I wanted to draw the bottom of Roscoe at that line, not the top. So let me see if I can keep my dude y. Like, I want my dude y to refer to the bottom of my sprite. So over here, I'm going to allow for the math to sort of like draw this my dude y as the bottom, like after the fact. So I don't have to think about like converting my dude y into where the computer needs the top of the sprite to be, because SSPR clearly is asking for the like top coordinate with this value here of where you want to draw the top of your sprite. And that's cool, that's how SSPR works, but I'm not beholden to that. I don't have to like put this in the top. It will actually make sense for my game that I'm keeping track of the bottom, and so to that end, I'm going to subtract from this value the height of our guy. So I'm just going to grab this height here that already has the scale times 8 and my dude age, and I'm going to subtract it from here. And so if we run this, there he is, just like standing there in the middle of the screen. So if we scale him, if we say let's do it 1 times, he's still standing at that bottom of the screen, but he is like way smaller. Okay, let's play a little bit with that. So I'll say, so here I'm going to use I'm going to make some decisions. If button up, then my dude scale, see it's handy already, plus equal to 0.1 end. It's already handy that we filled this scale into the my dude scale variable, because we can interact with it in our update cycle. So I'm going to increase the scale with the up button, and I'm going to decrease the scale with the down button. So now, whee! It always stays on that line. I can go below. Oh yeah, I can. Okay, so if I go into the negative values, it just like flips it in both axes, because that's what the math that we wrote does. What if we wanted to limit like what our scale was? Yeah, it's super easy to do with one line of code. So we can say, after we have like crunched what our buttons, after we have crunched the values that our buttons threw at the my dude scale, we can say that my dude scale is equal to mid. And so mid takes 3 values, and it will always return the middle value of the 3. So you can use it to establish the minimum and the maximum of some value. So I want my minimum to be 0.1, my maximum to be, say, 12, and the mid value, or rather the value that kind of moves around, is my dude scale. So if I run this, I can go smaller, I can go into negative, and I can go larger, 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 but eventually it'll stop. So it won't go beyond that point. So we have an interface with a minimum and a maximum value applied to a number that we're playing with. Let's change. Let's make it a little more kinetic. If button left, then my dude x plus equal to, I don't know, 0.1 times my dude scale. So that if we're it will enlarge it by a property of the scale, meaning that a bigger sprite on the screen will move a little bit faster than a smaller sprite on the screen, making it seem like zoomed in or something, as opposed to, oh, and this is wrong, because we want to add on the right and then subtract on the left. Okay, so right, left. So if the scale is clamped, let's see what that is. Ooh, that's too slow. A little faster than this. So let's do 0.5.